Poorly. Yeah, so that's why I'm going to give you a few more days. Has someone got the solution so far? No? Okay, I'll give you some hints here. What else to your joy next Wednesday, not tomorrow, but the coming one, I won't be here. I see you love me. And we schedule a makeup class some other day when we'll negotiate it between you and myself, right? Third, for the scribes, you have to download Gold International Phonetic Alphabet Fonts. There are thousands of them for both Mac and Windows. That's it, right? I'll leave a brief tutorial, a brief document with some pointers because I'm using to have problems to download or to install the fonts. We are supposed to be computer scientists, geeks. You know geek? Yes. Okay. So I shouldn't have given you lessons about this. Okay, so scribe, you? What? You'll read the scribe later. So today we will cover order relations, also called partial ordering. Or posets. So this is the last piece of theory. I recall what an order relation is: reflexive, antisymmetric, and transitive. And the idea is to sort elements set A. We are given a relation, an order relation. And first of all, I write that, which means that when I know this relation is of order, I just write this sign which is less or equal than in general. A couple of examples here. For example, the usual order relation on the set of integers. A is greater or equal than A, so it is reflexive. If A is less or equal than B, and B is less or equal than A, the only possibility is A equals B. And finally, A less or equal than B and B equals less or equal than C always implies A less or equal than C. That's very easy. Maybe I'm insulting your intelligence, or maybe not. The other example is divisibility. So A divides A, that's correct. A divides B and B divides A only happens when A equals B. We already proved that. And finally, A divides B and B divides C implies A divides C. It's already proved in class. Okay. No. So the first definition comparable elements. Comparable elements. I hope you know what either means. Either, you know either? I'll add it to the list, just in case. Either means like 4 or 5 things. Here is an equivalent to or. So or this, but in English the first time you write either. So either A is less or equal than B, or B is less or equal than A. This symbol here is a general symbol, and it doesn't mean order in the sense of real numbers. Okay, so I'll come back to, well, I'll come back to example 1. Example 1 there. So can you answer a question? Are every A, B comparable? When I'm talking about integers, can I say A is greater than B or the other way around? Yes, I can. No problem. No problem. And example 2, down here. Yes or no? Now my relation is divisibility. Right? It's not the usual ordering of integers. Can I compare any two elements in general? Yes? So let's assume your statement is true. 2 divides 3? No. So if your statement is true, then 3 should divide 2. That's false. So the answer is no. It's no. So you have an element that cannot be compared through your ordering relation. So total ordering, what's that? It's a partial order. It's a partial ordering where all elements are comparable. For example, this set here, set of integers with divisibility, is not a total ordering because none of its elements are not comparable. Whereas the set of integers with the usual ordering is. Okay. More things. Yeah, a little bit. A short poset, I'll be using this because it's very short, is partial ordered set. Poset. It's very, very used, and the book is using it as a main notation. Okay. The following will go in the exam. So case diagrams. So here we have a poset written in general form, and okay, I'm going to define it by example. So, in order to make a neat, clean diagram, I'll put one here. Because one is going to divide everybody else. So then I'll put 3 here, 4, 8, here I'll write 12 down, and 6. Okay. So I know it is a poset, it means it is a partial ordering. So first thing would be to draw the loops, right? So loops for everybody. This is reflexive. Yeah. And then I'm going to draw all the remaining arrows. So one divides everybody. Everybody else. So have that one. Right. Strive, wake up. And okay, then I will go to element 2. So element 2 divides 2, divides 8, divides 6, and divides 12. Then I will go to element 3, which divides 3 and 12. Then I will go to element 4, which divides 8 and divides 4. Well, that's kind of a mess. Am I done? No. What's missing? 6. Okay, so the haze diagram is a simplification of this cyclical diagram for partial ordering. So I'm going to simplify by doing the following. Remove loops. I'm going to copy this here. 1, 2, 8, 6, 12. Okay, remove loops. What else can I remove without altering the structure? What? I'm sorry, I didn't listen. Say it again, please.
The arrows from number 1 to the other numbers.
Every single arrow?
No, just
No, some of them.
You let the arrows to 2 and 3 because it's transitive. So we
Okay.
1 divides 2 plus 4 is 6. That's transitive.
Loops given by the transitive. Yeah. So in this case, it would mean the following. I don't have to draw it. This same thing here, the same thing here. I can remove this one, I can remove that one. Well, okay. Am I done? Or this is just too much deleting?
2 to 6.
2 to 6. Why can I delete this one? This one is not given by the transitive property. Only triangle, but this is not a triangle, that's a quadrilateral. Right? And the same thing applies here. Okay, you may have noticed that I didn't draw the points, the tips of the arrows. I don't need them. You know why? No? Okay. There is another convention here. So, well, the removal criteria are here, but I don't have a space. I'll write it down here. Right? So, here I see, for example, this element here, it just receives the arrows, right? And this element here is the origin of many arrows, but it doesn't receive any arrow. So this is going to be called initial vertex, and this is going to be called terminal vertex. Okay. So I see that there is a flow coming from 1 to 12 and end. So my convention is I'm going to remove the tips of the arrows when this is placed from initial vertices to terminal vertices. By the way, the vertex is an irregular word. It's plural, it's not vertex, vertices. So that's why here I can remove all the arrows. Because I go from initial to terminal. Right, upwards. And now what going on now? So I'm announcing that your exam will have to compute a case diagram, right? So you'll be given kind of poses, and you'll be asked to draw a case diagram. Or, yes, I'll be with you in a moment. Or you may be given some diagram, and you'll be asked whether it will be the case diagram of a certain partial ordering. Yes, please.
The word in the middle, what it is?
Upwards. En sentido ascendente. Upward, downwards. Like forward, backwards, upwards. Okay. So finally, we do that part. So I'm going to introduce four definitions: maximal elements, minimal elements, maximum, and minimum. So, and they are a little bit subtle. So, what's the maximum element? Say B. So it means there is no other element greater than B. Okay, that's easy. Minimal element that might be more than one is there is no A. A is less than B. Okay, so usually you work on the Hayes diagram because this is quite messy. So here, can you tell me one maximal element? 12. 12. And every single element is below. Maybe these two guys are not comparable, but the definition doesn't say anything about that. So the only thing the definition of maximal element is requiring the following. There is nobody else above this line. So this is maximal and maximal elements. What are the minimal elements here? Just one. Yeah, no two or three as I heard, because one is below 2 and 3. So this is the minimum. In this case, it's just one, right? Okay. What's the difference between maximal element and maximum element?
Maximum is just one.
Sorry, say it again.
The maximum element is just one.
It's just one?
Yeah. And this the biggest element.
Yeah.
The maximum element.
Yeah. Yes. The difference is here. It says for all. So what was the maximum here? No. Think twice. Yes. Go to the definition. What's the maximum element here? There is none. Because it says that B must be comparable to all elements. It says for all, this for all is really crucial, it is of paramount importance. So there is no, I didn't state, but you thought I would, that the maximum always exists. No. Some sets may not have a maximum element. In fact, they may not have maximal elements. When you have infinite, what's the maximum? For example, this set with the usual order. What's the maximum element? There is none. The maximum, there is none. Minimal, there is none. Minimum, definition down in a second. None. Right? So here, for this set, there is no maximum. Finally, minimum element B and here, yes, we have a minimum because this guy is related to everybody else and it is below everybody else. So in this case, well, it is clear that the maximum is a maximum element, the minimum element is a minimal element, the other way around is false. So if, for example, that's a nice question. If I say to you, this set, this whole set has both maximum and minimum, what the shape of its H diagram will be? Again, if I say to you, okay, here you have a poset with maximum and minimum elements, what would the shape of the H diagram be? It would have something here, like that. Yeah, I don't know. And at the end, it would have a center. Here in the middle, it may be very complicated, but I know it has to have like a summit. I have to have an apex here. Right? Okay, this is not very complicated. Okay, that's all the theory I want to cover today. And also it's all the theory in lesson 2.